Hello students, welcome to today's lecture on advanced concepts in discrete time Markov chains. Today we will talk about events which will require us to calculate hitting probabilities and return and exit times. So let us begin by looking at the definition of hitting probability. We define a random variable, capital T sub A, as the first time the Markov chain, denoted by x sub n, hits the set A starting outside the set A. That is, mathematically, we would want to find the minimum n, where n greater than or equal to 0, given that x sub n is within the set A. Clearly, T sub A is equal to 0 if x naught is within A. Because if we are already inside the hitting set, the set that we want to hit, we don't have to go anywhere. So T sub A, the time is 0. And if this set, whose minimum we want to find, is a null set, then we would never hit that set A, right? So T sub A would then be infinity. So the question then is, what is the probability of hitting set A through some state L, which is part of A, starting from a given state S? So symbolically, we would define that or denote that as probability P of x sub T sub A equal to L given x naught equal to K. And we call that G sub K of L, where K is the starting state and L is the state we land up when we first enter the hitting set A. So G sub K sub L, as is defined in terms of the probability, is P of x sub T sub A equals L given x naught equal to K. But that could happen through many disjoint ways. And we need to add up the probabilities of each of these disjoint ways, right? So we would then do that by considering the probability that x sub T sub A equals L and x sub 1 is equal to M, given that x naught equal to K. That is, the first step that we have taken is equal to M, and M could be any of these disjoint events. And we will have to compute this conditional probability. So then we use the law of total probability, and that expression turns out to be the sum of all these probabilities, which are probability of x sub T sub A equals L, given x1 is equal to M and x naught is equal to K, times the probability that x sub 1 is equal to M given x naught equal to K. This is just a statement of law of total probability, which we have seen much earlier in the course. Then we will use the Markov property, which is if we know x sub 1 is equal to M, it doesn't matter what x sub naught was, so we'll ignore the x sub naught equal to K from this expression, and we'll be left with this expression, which reduces to summation of M belongs to S, P, little p coming from the stochastic matrix, capital P, so P sub Km times G of M L. So this is a nice recursion relation which we could use to compute the hitting probability. The next thing that might concern us is mean hitting time. How much time, how many steps do we have to take before we actually hit this state or set A, which we define here by 8 sub K of A as the expected value of T sub A, which is a random variable, given that we begun from the state K. Clearly, if we are already inside the set, there is no need to go anywhere and the mean hitting time is just 0. So we'll consider the case where K, the initial state, is not inside our target set. So we are in S minus A. So we are interested in finding the expected value of T sub A given x naught is equal to K. So that would again be the sum of these disjoint expected value calculations, because we could make the first step to m, where m could be any of these disjoint cases. Then we would apply the law of total expectation, which will enable us to write the summoned as expected value of t sub a, given x sub 1 is equal to m and x naught is equal to k, times the probability that x sub 1 is equal to m, given x naught equal to k. We then use the Markov property, ignore the effect of x sub naught equal to k, and retain just x sub 1 equals m, because that happens to be the most recent information that we have. And then we'll again end up with a recursion relation, which is h sub k of a equals 1 plus summation of m plus m belongs to s of p sub km times h of m a. Now, where did this 1 plus land up from? That's an interesting question, right? But remember what happened. We started with the calculation with the 0th step, and using the Markov property, we were able to ignore the 0th step after having taken the first step in m distinct ways, right? But we need to account for that step that we just took from going from x sub naught to x sub 1. So we need to add that, right? That's where this 1 plus comes from. So this is again a recurrence relation that you could use to calculate mean hitting times. Likewise, we have return times. Let's say we begin with some state, and how long does it take us to come back to that state, right? We denote that by the random variable t sub y of r for return, but we sometimes ignore r because if it is understood, we need not write r, which is the minimum of n greater than or equal to 1, given that x sub n is equal to y, right? Y belongs to s. Okay, so I will not go over the calculation of the mean return time to state y starting with state x, because it follows very similar steps that we just went over in the previous 2 slides to calculate the mean hitting time and the probability of hitting a given state. But I will just mention this relation here, and I would ask you to do this, work this out as an exercise. So mu sub x of y is the expected value of returning to state y beginning from state x, right? And that turns out to be another recurrence relation given by mu sub x of y equals 1 plus summation over p sub x of m times mu of m of y, where the summation runs over all m in the state space, which is not equal to y. And in particular, the return time beginning from that state, mu sub y would be the same expression, just replace the x by a y. So this will become clear if you look at an example, and I'll give you the sketch of the solution and I actually ask you to work this out in more detail. The question here is, let's say we have a game of badminton. We have a court which looks like this in the picture, where each side is divided into 2 sections. So section 1 on the right, section 2 on the left. And let's say in this game, a service begins from section 1. We would want to know when does the shuttle return to section 1 on an average. Remember, we are finding expected value, so this is all on statistical average. So when does the shuttle return to section 1 on either side, beginning, given that the service happened from section 1? Let's say we have calculated the data from many badminton games, and we have the probability transition matrix given by bold P. So we would write down the recurrence relation for mu sub x of y. In this case, we would write down mu sub 1 of 1 in terms of p1 of 2 and mu sub 2 of 1. And we would write down the expression for mu sub 2 of 1 in terms of p of 2, 2, and mu sub 2 of 1, just by using the recurrence relation boxed here. And after some very simple algebra, we will recover that mu sub 2 of 1 is 3 and mu sub 1 of 1 is 2. So on an average, it'll take 2 shots before it comes back to section 1. So that's kind of a neat way of looking at return times of Markov chains. Thank you so much.